All right, guys. So this is Miss White after school doing your Zoom that I cannot do live with you guys, but I'm just going to walk through the study guide. I got like 30, 45 minutes to do this. If there's something I miss and I don't have time for, I can come back and do it later. I can also meet up before school if anybody has questions then, and I can also record that if you just want me to do more problems. Nobody emailed me for questions on this, so I'm just kind of going off of what I think is important and questions that have kind of been asked during class. I'm going to do as much of this as I can. If I can do it on this right next to the problem, awesome. If not, I'm going to scroll down and you will just have to kind of keep track of those problems. So starting at the beginning, anytime we're arranging something or doing factorial, so arranging, batting orders, anything that we're like putting something in a line or in a circle, even anytime it matters the order we do factorial, that's exclamation point. So in how many ways can we arrange the letters in the word precalculus? First, we think about how many things are we arranging? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I've got 11 letters. So I'm going to do 11 factorial. That's how many items I'm arranging. There's no groups or bundles or anything. There's no, it's not like a necklace where I have to flip it over and divide by 2. What I am going to divide by though is the letters that repeat and are the same. So like if I see something more than one time, I have to divide the repeats off. So I don't see any more P's. I don't see any R's. I don't see any more E's. I'd have 1, 2 C's. So I've got to divide by 2 factorial. No more A's. I do have 2 L's. So I'm going to divide by 2 factorial. And I have 2 U's. So 2 factorial. So my whole answer is 11 factorial divided by 2 factorial times 2 factorial times 2 factorial. That's the best answer. That's the best way I want you to write it. Okay. The next 2 are problems that are dealing with P's and C's where we're picking and choosing, chosen, all that stuff. That's not your key word, but it helps me know that I'm picking a small group from a big group. When you're picking a small amount of something from a bigger total, that's using your P's and C's, P and C. P is where order matters and C is where order doesn't. So in these 2 problems, they're basically the same. It's not a great example, but captain versus assistant captain. That's like a coach versus an assistant coach. Those are 2 different titles, right? So that matters whether you are the captain or if you're the assistant captain. So we're going to call that P. The total of people that I can choose from is 10, and I'm choosing 2 things. I'm choosing a captain and an assistant captain. So we're going to call that 10P2. Again, if you missed it today, this setup is most important to me. If you want to plug these in the calculator, go for it. But this is what I'm going to grade anyway. So this is essentially what I'm looking for. If you do put that in the calculator, that's 90 different ways. Now, the next one says it's the same situation. So you still have a team of 10, but this time we're taking 2 co-captains. If you're co-captain, your job is the same. It doesn't matter if I say you first or second, you're just a co-captain. So order doesn't matter here. So this time it's 10, choose 2. And again, if you want the actual number for that, that's 45. The number for C is always a smaller number than for P, because if order matters, I can say like 1, then 2, or I can go 2, then 1. So that's why it kind of doubles that amount. Number 4 is another being seated or arranged. They're in a row, that's a line, so that's just 5 factorial. All right, number 5, I had a lot of questions on this during class. So hopefully most of you got it answered during class, but I'm going to talk about it now. So I have 5 algebra books and 6 geometry books. We're arranging them. All of these situations are different. So for situation A, all of my books are different. So I've got 5 unique, special, different algebra books and 6 unique, different, special, unique geometry books. So I always think about how many items am I arranging? Then I think, is there any bundling? And then I think, are there any repeats? So there's no bundling, there's no repeats. They're all different, they're all unique. I'm physically arranging 11 items, 11 books. 5 plus 6 is 11, okay? Letter B, all the books are different and must be with their own subject. Okay, so I have to keep all of my geometry books together and I have to keep all my algebra books together. That means I'm not arranging 11 different items. I'm really only arranging 2 items. I can either have geometry and then algebra, or I can have algebra and then geometry. So the amount of items I'm organizing or arranging is just 2. So it's 2 factorial. Now, within those 2 things that I'm organizing, I can rearrange the books as much as I want. So then within my geometry, I have 6 books that I'm arranging. So that's 6 factorial. And then within my algebra, that's 5 books I'm arranging. So that's 5 factorial. So this goes 2 factorial times 5 factorial times 6 factorial in whatever order. It's multiplication. It doesn't matter. Okay. There's no repeats, nothing. So I'm going to not divide by anything. Letter C says all the geometry books are identical. It doesn't tell me anything has to be together. So I ask myself, how many items am I arranging? I'm arranging all the books. There's no other notice on what else I can do. So it's going to be 11 factorial. But this time it tells me the geometry books are identical, which means if I have these 2 geometry books and then I switch them, but everything else stays the same, if they were identical books, then the bookshelf would look different. Or sorry, if they were unique books, if they were different, if I switch their places, the shelving would look different. Since they're the same though, it doesn't look any different because I switched these identical books. So we're going to divide by all the repeats, and there are 6 geometry books. And so I'm going to do 11 factorial divided by 6 factorial. The last one is geometry books are identical and must be kept together. So this is kind of combining B and C. Okay, so geometry books are identical and must be kept together. First, I'm thinking, how many items am I arranging? Only the geometry books must be kept together. The algebra books are on their own. They can do whatever they want. So that means I have 6 things that I'm arranging. 1, 2, 3, 4, 5 algebra books plus 1 set, I guess, of geometry books, 1 bundle, 1 clump of geometry books. So I've got 6 things I'm arranging. Now, within that 1 clump of geometry books, there are 6 different ways that I can organize the individual geometry books. However, I also have to divide off my repeats, and my repeat is the 6 geometry books because they're all identical. Technically, we get all the way down to just 6 factorial. I don't want to make any general rules about like, oh, well, since they're kept together and they're identical, you don't need to include that. I'm just kind of considering every single thing I always do. But if you do want to simplify it, the 6 factorial goes away. Again, there are 5 algebra books and 1 clump of geometry books. So I've got 6 things that I'm organizing. And within my clump of geometry books, you can organize those 6 factorial different ways. Okay. Number 7 says, in how many ways can 5 or 4 red beads, 6 identical green beads, ooh, identical seems like an important word, and 2 yellow beads be arranged to make a necklace? Okay. There's no clasps, so we're going to assume that it doesn't say anything about clasps, so we're going to assume that there's no clasps. Oh, shoot, I skipped number 6, sorry. In how many ways can 6 kids be seated in a row? 6 factorial. Ooh, let's ramp it up. Let's ask ourselves another question. How many ways can 6 kids be seated in a circle? Do you guys remember how the circle ones go? It's whatever the number of people there are or things there are minus 1. So if I have 6 kids, when I minus 1 off, it's 5 factorial is how you can seat them in a circle. Okay. All right, so I've got these beads. I remember, I might have to go back to my notes to check on this necklace problem, but I remember that we did the total number and then we divided it by 2 because it was a necklace, which means that I can like have it one way and then flip it the other way and it looks like things are in a different order. So I got to get rid of that because it's the same order, it's just flipped. And then I also have to minus off the identical beads. Now, if it's in a necklace, it doesn't say anything about a clasp. So I'm going to assume that I'm arranging these in a circle. Wow, I'm so glad I just thought about doing the circle a minute ago to remind us. So that means my top isn't going to be 4 plus 6 plus 2. It's not going to be 12. It's going to be 11 factorial. Because when it's in a circle, you think about 12 minus 1 factorial. That goes there. Again, if it was a clasp, if you clasped your necklace, then you can line it up in a straight line, but it doesn't say that. So I'm going to assume that there's no clasp. So that's why it's in a circle is how I got 11 factorial. I always divide the necklace ones or like a keychain one, anything that you can physically pick up and turn over, like my hands, like I'm trying to do a demonstration. I don't know if you can see my picture, but like my thumb is like closest to me here. But then when I flip my hand over, my thumb is the farthest away. I can't physically rearrange how my fingers go, but it looks different, but it's the exact same organized. It's just flipped around because I could manually pick it up and move it. So I divide by 2, and then I also divide by any repeats. The only repeat I have is 6 identical green beads. So I'm going to do divided by 6 factorial. So 11 factorial divided by 2 times 6 factorial is my answer for how many ways we can arrange this necklace. Okay. If you have any follow-up questions, I would really suggest you come to see me tomorrow morning. Okay. I'm going to copy these number 8 and 9 down because this is 9.2. This is that binomial expansion Pascal triangle. I'm going to write that down below. Hopefully I've got some space. Oh God, I've got a ton of problems. Okay. We'll do it down here. Here's where my work goes. Okay. So first things is I don't need Pascal's triangle for the first one. So I'm going to do the first one over here. When you're finding, I don't know why it says team, third term of this set. Okay, whenever we're doing terms, you think about the first number and that goes down an exponent. So I'm going to start with the biggest exponent and then I'm going to go down one each time. So I would be at x to the 10th, then I'd be at x to the 9th, then I'd be at x to the 8th. So my third term is going to be whatever the first term is raised to the 8th. So I think of that as 5x raised to the 8th. Now, I don't have my second term in here yet, and those exponents must add to be 10. So instead of going backwards or anything, I just know that when I'm on this term, when I'm on my third term where the first term is being raised to the 8th, in order for my exponents to add to be 10, my second term must be raised to the second. 8 plus 2 is 10. Last thing is there's a coefficient that goes out front here. Normally when it's a smaller number, we're going to use Pascal's triangle, but I'm not going to give it out to you to 10, and I highly suggest you not going all the way out to 10. We're going to use n choose r right here. So just like we did co-captains above, we're going to do n choose r here. The first number is the total exponent that we have. The second number is the exponent of the first term. So it goes 10, choose 8. Okay, 10, choose 8. And then I could multiply this out a little bit more. Again, this is what I'm mostly looking for the work, but if you want to go one more step further, you can. Thanks, Will. It's right there is perfect. Thank you, Will. And I'll get your the desk in a little bit. So again, you can multiply this out or you cannot. Bye, Will. What I'm going to do is just leave it here. The next one, we are going to use Pascal's triangle. So let me remind you what that looks like. So Pascal's triangle, it always goes 1, 1, 1, 1, 2, 1. I'm building this by just adding the terms ahead of it. There always starts and ends with 1, but then like the next term comes from the addition of 1 plus 2, and that gives me 3. 1 plus 2 here also gives me 3. Again, I don't expect you to know how to do this. I'll give it to you. That's 4, 6, 4, 1, and this is 1, 5, 10, 10, 5, 1. Now this is as far out as I need it to go, and I'll just go as far as I want you to go. I'm not going to give you out to 10 because on this one, again, you can use 10, choose 8, which is the total exponent and then the exponent of the x that's there. And, but for like anywhere from 3 to like 5, I'll probably ask you to expand out this way. When I expand, I have to think about my coefficients. I have to think about my first term. I have to think about my second term. So my coefficients are here. I've got 1, 5, 10, 10, 5, 1. Got a little ambitious there. Okay. Then we're going to do our first term and we're going to do decreasing exponents as we go. So I'm going to start with 2x to the 5th and I'm going to go down as I go across the page. So this one is 2x to the 5th. The next one is 2x to the 4th. Then I've got 2x to the 3rd. Then I've got 2x squared, and then I've got 2x. You should have an extra one that doesn't have anything. That's technically 2x to the 0, which is just 1. I'm not putting any more ones that I have to. Okay. Then I do my second term, and I always am increasing that. So I start at the very beginning, and I just add my second term in, and I want my exponents to add to be 5. So I don't have one for the very beginning. It's just the first term raised to the 5th. But the next one's to the 4th, so I can have a y in here. And it's just plus y, so I don't need to be super careful with exponents or anything. Y is literally my second term. Same thing over here. This is going to be y squared. This is going to be y to the 3rd. This is y to the 4th. And this is just y. And then we're adding all of these terms together. Plus, 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 plus. And I do want us to multiply or factor or whatever, all of those out so we can get to what we need to get to. I think I've got these numbers down. Oh, sorry. Okay. So 1 times 2 times x to the 5th. So 2 to the 5th is going to be 32. X to the 5th is x to the 5th. The next one, I've got 5 times 2x to the 4th times y. So 2 to the 4th is 16. 16 times 5 is going to be 80. X to the 4th, y. Then I've got 2x to the 3rd. So I'm going to do 2 to the 3rd. That's 8. 8 times 10 is also 80. X to the 3rd, y squared. Then I do 10 times 2x to the 2nd, y to the 3rd. So 2 squared is 4. 4 times 10 is 40. X squared, y to the 3rd. Then I've got 5 times 2x, y to the 4th. 2 times 5 is just 10x, y to the 4th. And then it ends with, oh, I forgot my 5th, y to the 5th. So I expanded it out. It's really big now that I've expanded it all the way out. But make sure that your coefficients are right. Make sure your exponents are all right. And I double check myself. It goes x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x, nothing. And then y's, it's got y0 as the first term, and then it goes y, y2, y3, y4, y5. That works out. Okay, that's my expanding. I almost asked you guys if you had questions, but you cannot talk back to me. So if you have questions, come see me in the morning. All right, number 10 looks more difficult than it is. How many different lunches are possible if you eat a sandwich, a piece of fruit, and a drink? Okay, so there are 6 different sandwiches. You have to eat one of them. So I can think of that as 6, choose 1. Just making sure that's right. I think that's right. Same thing with a piece of fruit, piece of drink, whatever. You also can just think of it as like, there are 6 options, there are 4 options, there are 2 options. So I'm just multiplying all of the options that I have. There's no factorial because you're not arranging anything. There's no dividing off because there's no repeats. This is a lot easier than you think it is. So this is like the one on the notes where it's talking about like different outfits. If you have like this many shirts and this many pair of pants. So we're just doing 6 times 2 times 4. And that would be 48. Okay. The next couple are choosing from a group. So 5 people in a race, the top 3 finishers will receive $25. Does it matter who's first, second, or third? No, they all get $25. So this is a C. I'm going to do, how many people are there? 5 people, and we want 3 finishers. So we're going to do 5, choose 3. Okay. Next one, from a group of 8 different sodas, how many weight can groups of 5? So you have 8 sodas, you want groups of 5. It doesn't matter what first, second, or third. This is another choose. 8, choose 5. From a list of 5 books, how many groups of 2 can be chosen? It doesn't say which one you're going to read first, which one you're going to read second. It's just a choose. 5, choose 2. Order does not matter. All right, this one's fun. From a group of 4 men and 5 women, how many committees of 3 men and 2 women could be formed? Okay. So we have 4 men, we've got 5 women, we want 3 men and 2 women. So you are going to have 2 different chooses here. Again, it doesn't order doesn't matter. Sorry, guys. End of the day, I've got no words. Hopefully I don't mess up too much more, but order doesn't matter. It just matters that I get 3 guys and I get 2 girls in. So when I choose this, I'm going to think about it one at a time. So I'm going to do the men first. So there's 4 total men and I want 3 of them. There's 5 total women and I want 2 of them. Now, I can't have a full committee unless I have the 3 men and the 2 women. So this makes one whole like successful outcome. So we're multiplying them together. If I said, well, I can have 3 men and 2 women, or I could have 4 men and 1 woman, or I could have, those are different types of committees. This is all just like one committee. This is what you need to be successful. That's why you multiply. If there's a couple different options, then we add them. Okay. Number 15 is kind of like that M&M one we did back in 9-3, where you could make a little chart, but we could also just do chooses from them. So I've got number 15. So I've got a bag. One bag contains 3 red, 5 green, and 8 blue marbles. And we want to choose 2 red, 1 green, 2 blues. Again, it says choose. We're choosing them. I think I see with that. So from their 3 red ones, we want 2 of them. 3, choose 2. This does not say what's the probability, what's the percentage, what's the probability is a key word. This says in like how many ways can this be chosen? So we're just choosing. Okay, there's 3 marbles and I want to choose 2 of them. Okay, there are 5 green ones and we want to choose 1 of them. There are 8 blue marbles and we want to choose 2 of them. And again, I want all of those things to be true at the same time. So that's why I'm multiplying them. All right. Number 6, I feel like we've done already. Or 16, how many ways can 6 people line up? We literally did that a minute ago. How many ways can 6 people be chosen? I don't know what they're chosen from. You can ignore those 2 problems. One of them's a repeat and one of them's kind of a dumb question. I don't know. There must have been something else I was thinking about last time. All right, an ice cream shop has 8 different toppings. You get 3 on a sundae. How many different combinations are there? Again, doesn't matter what order. It doesn't matter if you put the sprinkles before the peanuts or if you put the chocolate chips before the syrup. Like, I don't care what it is. You can't, doesn't matter for the order. So I do 8, choose 3. There are 8 people for the final of the 100 meter in the Olympics. How many ways can the gold, silver, bronze be awarded? Ooh, let's pause. Gold, silver, and bronze are very different. We just flew through a bunch of combinations. These, it actually matters. It's different if you get gold versus you get bronze. I mean, anyone who's been there feels that, right? So this time it's not, what is it? 8, choose 3. It's going to be 8P3. We're picking 3 because order matters here. It matters who gets picked first. Okay. Next one, a 4-person committee chosen from 13 people. Does order matter? No. 13, choose 4. Okay, fun. Now we're ready for some cards. Okay. We're doing cards and they all say we're finding, this little P means that we're finding the probability of these things happening. Okay, so first thing we need to figure out what's the like total probability of choosing 2 cards from a deck. Well, how many cards are there? 52? When you have like a hand of cards, does it matter that you got like what, like the jack first and then the 10 later? No, it just matters that you have both a jack and a 10 in your hand. So that means order doesn't matter, so it's C. Whenever we're doing this with cards, remember in class we did a bunch of examples with 5-card hands. This is 2-card hands. It's the exact same thing. In class, we were dividing everything by 52, choose 5. These are all going to be divided by 52, choose 2, because I'm only choosing 2 cards. Okay. So all of these are going to be over 52, choose 2. So the first one says both aces or both black. Okay, so we have options. So how many aces are there that are fine? Well, there's 4 total aces, so we want at least 2 of them. So I'm going to think of that as 4, choose 2. It's also okay, so that's an okay hand, but I could also be okay if they're both black. Okay, so that means I could do, there's how many black cards? 26. Ooh, but we already used 2 of them, right? We already thought about the aces being black, so we can't have the aces being in there. Let's do it this way. Let's do 26, choose 2, but we're going to minus off the intersection where I've got black aces. And that's just 2, choose 2. I don't know what I'm drawing there. 2, choose 2. So we took care of all of the aces, we took care of all of the black, and then we just minus off the overlap, the connection between them. And that's all being divided over 52, choose 2. Okay. Then I've got both 3s or both face cards. Okay. Again, same idea. Both 3s. Okay, there's how many 3s? 4 3s. So I'm going to do 4, choose 2. And then there's how many, what was it, face cards? Jack, king, queen. There's 4 of each, so that's 12. 12, choose 2. Is there any overlap between 3s and face cards? No, right? They're not the same. One's a face card, one's a 3. That doesn't work that way. Okay. So I'm going to divide that by 52, choose 2. All right, last one says both black or both kings. Ooh, this is going to be an overlap like the other one, okay? So let's do that one over here. So both black. Okay, so that means there's 26 black. We want to choose 2. We could also do a king. A king is fine, so that's 4, choose 2. And then we got to count the overlap. There are 2 black kings, and we can't count them twice. So we're going to count minus off 2, choose 2. And all of that, again, is over 52, choose 2. Another key word, I had minuses and pluses in this because those are all different hands that are okay. It's okay to have an all black hand. It's okay to have an all king hand. Those are different. They don't have to be the same. They don't have to go at the same time. So because it was or, that's why I did plus. If it said I need a black card and a king, well, those are 2 different cards that I need in one hand to be successful. So like I would be successful if I had all aces, and I would also be successful if I was all black. So that's why we looked at those. Okay. That's super similar to the next one. I can run through that really quick. It says all red or all black. Okay, first we got to think about the total probability of choosing 3 pens at random. How many total pens do you have? 4 plus 9 is 13. 13 plus 7 is 20. So 20, choose 3. So I've got all red or all blue. All red is 4. So I'd say 4, choose 3 because I'm choosing 3 pens. Or all blue is also fine. So plus 9, choose 3. You don't have to divide anything off, or sorry, you don't have to minus anything off because there's no overlap. There's no pen that's both red and blue. But we are going to divide off the total, the 20, choose 3. Now, the next one is going to be interesting. This one we're multiplying because we want at least 2 blue. So we can have a couple different options. Okay. All of it's over 20, choose 3. We could have 2 blue pens. So we could have 9, choose 2. And then times the rest of the pens, choose 1. The rest of the pens is 11 because it's 4 plus 7. So it's 11, choose 1. Because I still need 3 pens. I'm selecting 3 pens. So I want 2 of them to be blue and then 1 of them to be a different color. It's also okay though for me to get it says at least 2 blues. So there's another option. Actually, if I was done, that would be the answer for letter C. So let's actually just change my arrow because this is exactly 2 blue pens. I'm going to take this though and build off of it for letter B. So letter B is 9, choose 2 times 11, choose 1. And then plus there's another option. Oh, I did my arrow wrong. Oh, shoot. Plus. My arrow should go all the way up to B. I also could have not just 2 blue pens, but 3 blue pens and no other color. So I'm going to do plus 9, choose 3. And all of that's over 20, choose 3. Okay, I'm actually going to pause this for 1 second and I'm going to come back. Hopefully this doesn't mess up your guys' recording. oops, I stopped my share, not my recording. Okay, well, I'll see if I can cut that later. If you're still watching that, I hope you fast forward 3 minutes, or I'll put notes to fast forward 3 minutes. I had to step out for 1 second. So that was page 1. We're gonna keep going and see what we can do on page 2 and page 3 and 4. I got like 15 more minutes. All right, I've got these, what are they? This is 9495 kind of stuff. So you can use that to help you know how to answer these problems. 9495. Determine if it's arithmetic. Remember, arithmetic means that we add or we subtract to get to the next term. If it is, then whatever we add or subtract is the common difference. We want to find the term named in the problem, and we want to find the explicit formula. So let's do, I think this one, number 4, is going to be a fine one. Let's double check. So I'm just checking to see if it's arithmetic, which means I add or subtract. So to get from 15 to 23 is to be plus 8. If I do 23 plus 8, that's 31. And if I do 31 plus 8, that is 39. Okay, perfect. So this one is arithmetic. So I would write yes next to it. And my a sub 1, my first term is 15. My common difference is 8. And I want to find a sub 20. So remember the common form. And again, I'll give this to you, is going to be a sub n equals a sub 1 plus n minus 1 times d. So a sub n, I'm going to find a sub 20 equals 15 plus 20 minus 1 times 8. What I'm about to find is a sub 20. I know I plugged 20 in for that n, but a sub 20 is still a variable. It still is like the 20th term, and I want to actually find out what that term is. So I'm going to do 20 minus 1 is 19, 15 plus 19 times 8. 19 times 8 is 152 plus 15 is 167. So a sub 20 is 167. I also could ask you for the explicit formula, which I might have in this type of problem. And I'm going to essentially use what I had right here, but I'm not going to have 20 for my n. I'm going to keep it as n. So I'm going to do a sub n equals 15 plus n minus 1 times 8. That's my explicit formula. Okay. I think I've got a decent answer key for this, so you can check that out later, more problems like that. Let's go to the next page, or not next page, next set of problems. I'm going to do the exact same thing, but it's geometric. Let's do, we'll just do number 6 because it's right above it. To get from 3 to negative 6, we multiplied by negative 2. Same thing to get to 12 and to go 24. Perfect. So that's my R. In geometric, we call it R. So I've got a sub n equals a sub 1 times r n minus 1. So this time I want to find a sub 12. My first term is 3. My r, my common ratio, is negative 2. And I'm doing it to the 12 minus 1. 3 times 2 raised to the negative 2 raised to the 11th. Just a little helpful hint, when you are raising a number to an odd exponent, then it stays whatever sign you have. So I'm about to raise a negative number to the 11th power. I just can do 2 to the 11th and know that that's going to be a negative number. Anything you raise to a positive or to an even exponent is going to be a positive number. So I've got to do 2 to the 11th and then do 3 times that. 1, 2, 3. Okay, I hope I didn't mess it up, but I think it's 2048. And then I multiply that times 3. And again, it's negative because it was an odd exponent. So it's negative 601.44. Yeah, that's right. 6,144. That's my answer. And that's right. I just checked the answer key. Remember, I could also ask the explicit formula. So we just take this part right here, but get rid of my 12. So I've got a sub n equals 3 times negative 2 raised to the n minus 1. And that's also an answer. Okay. Again, you can see more like that on here. Evaluate each arithmetic series described. This is actually an easier way than the problem we did in class today. Arithmetic series is those S of n. So it's arithmetic, so it's that first one, S of n equals n divided by 2 times a sub 1 times, or plus a sub n. I just gave you all the pieces. We just plug it in. So like, let's say I look at number, I don't know, 11. We're going to do 35 over 2 times 1 plus 113. I plugged a sub 1 in for 11 in for a sub 1. I plugged 113 in for a sub n, and I plugged n 35 in for n. So I'm going to do 11 plus 113 times 35 divided by 2 is 2,170. I'm going to do the exact same thing with the next set. So I can give you super easy pieces like that. The geometric series is, again, what we went over today. That formula, though, is S of n equals a sub 1 times 1 minus r to the n all over 1 minus r. I did write these nicely earlier today and in class. So hopefully if you're like, what is she writing? You have a nicer version somewhere else. We'll just do number 13 for this. So I'm going to do negative 3 times 1 minus negative 4 to the 7th over 1 minus negative 4. All right, I'm going to zoom in on that so it's not so messy. All right, so I have to do negative 4 to the 7th. So I've got negative 3 times 1 minus whatever that number is. And then I've got 1 minus negative 4, which is 5. So 2, 3, 4. Okay, I think 4 to the 7th is 16,384. And that would still be negative because it's being raised to an odd number. So minus that becomes a big plus. I would have minus and negative with these two negatives, which becomes a big plus. So I do 1 plus that. I multiply that by negative 3. I divide that by 5. And I get negative 9,831. Yes, and that's the right answer. I know my work's in for number 14, but it's number 13's problem. Again, all we just did was plug and chug. All right, and then the last thing on this page is evaluating the series. This is summation notation. We did a problem like this in class, and I told you you were responsible to know how to do this. So we're gonna go over that. Let's see, number 18 looks like the hardest one. All that's happening here is that we're gonna plug different numbers in for A. We're gonna start with 1, we're gonna do 2, we're gonna do 3, we're gonna do 4, and we're gonna go all the way up to 5 because the top number is what tells us to stop. So you're essentially doing 4 times 1 squared minus 3. It's summation. This is a big sigma, which means sum, so it's plus. And then 4 times 2 squared minus 3. And then plus 4 times 3 squared minus 3. And then plus 4 times 4 squared minus 3. And I've got to do it one more time because I got to go all the way up to 5. 4 times 5 squared minus 3. Now, you can plug those numbers in. I'm not going to hold your hand through that. That should equal 205. But that's summation notation. The little e means to sum, so that's why I have them all added together. Oh, that's not the add. Added, added, added. And then each time I'm plugging in 1, then 2, then 3, then 4, then 5, and I just go until it tells me to stop. All right, so that's page 2. All right, let's do some probability. Let's see. You don't have to worry about this diagonal unless you want to do that. Don't have to do that. It looks like this problem looks like a Venn diagram, I think. Yeah, let's do that one. And then there are some up here. I think we'll probably do this deck of card one and then maybe another one. I don't see any of those factor tree ones. where it was like percentage, it's like 30% chance it's going to rain. And if it rains, then Ryan does his homework 10%, whatever. We're going to do, I can look at that later. So I can make another video if anyone requests that and wants to see it. But let me do these couple problems and then I will probably call it a day for today. Again, I can do more tomorrow morning, or if you email me later, I might have time to do it tonight. Depends on how I feel. Okay, so this says in a school, I'm looking at number 9 on page 4. I'm doing all that work down here. It says in a school, there are 450 seniors, 335 of them are taking math, 287 are taking science, 220 are taking both. So we got to do our Venn diagram. So there's a total of 540 students. Let me move this guy over a little bit. There's a total of 540 students. I'm putting that on the outside. And then I've got science bubble and I've got math bubble. And it says there's 220 taking both. So that means the crossover is 220 right in there. And then it says just science, or all the students taking science is 288, 287, 287. So in that yellow should be 287. Well, we already have 220 in there. I know that that overlap seems really small. I didn't draw it to scale. But if we minus off 220, that should tell me how many are just taking science. So, sorry, but I could do that in my head. My brain does not want to do that. I get 67. So there's 67 kids in the science part. And then math, what did it say? There were 300 something? 335 of them taking math. And again, minus off the kids in the middle, minus off that 220 is 115. And then the last thing before we even look at the questions, I want to do how many are not taking either. So we're going to add the 3 numbers we see. We're going to add 67, 220, and 115, and then minus that from 450 because all inside this box should be 450. So 115 plus 220 plus 67 is 402. So 540 minus 402 is 138. So there's 138 students not taking anything. Okay. How many seniors are taking neither math or science? Oh, thank God we just found that, right? Letter A is 138. And again, we added everything up and we minus from 540. 67, 220, 105, 115. Letter B asks, if the senior is selected at random, what's the probability he is only taking math? Okay, so probability is like number of success over total. So we're going to divide by 540. And it says he's only taking math. So how many kids are only taking math? 115. So 115 divided by 540 should be the percentage that this kid that we choose at random in the senior class is taking math. If you were to do that out, that would be 0.213 or 21.3%. All right. You can look at your notes to do more examples like that. I would bet money on there being a Venn diagram, either one you have to draw or one that I draw for you and you answer questions. I'd bet money on that tomorrow. Okay. Let's keep going. Let's come back up here and let's do, again, I've got the answers for this. I hope they're all right, but we're gonna do these. Let's do number 2, and I'm actually gonna copy and paste this and put it down below. We did ones like this before. Oh, no, come on. Probably all I'm gonna have time for. Okay, what's the probability you will choose at least one king? So we are choosing 5 cards from my standard deck. So again, like we did in class, that's gonna be 52, choose 5. I'm not explaining why it's C versus P in all of these problems. This is my general explanation. It doesn't matter what cards are in your hand as long as they're there. So it doesn't matter the order. So probability that you'll choose at least one king. So I can choose 1 king, I can choose 2 kings, I can choose 3 or 4 or 5. Whew, that's a lot of options. I'm like tired explaining that. What I can't have though is 0 kings. So I'm going to do 1 minus what's not okay. Remember we did that in class a couple times? Instead of doing the option of 1 and of 2 and of 3, I'm just going to say, okay, what's the probability I can't choose any kings? The probability of choosing no kings is going to be how many cards are not kings? There's 4 kings, so minus that from 52, that's 48. So I've got 48, choose 5 over, is that right? Give me 1 second. Yeah, 48, choose 5. So that's just all cards that aren't kings over 52, choose 5. So it's not okay to have all not kings. I know there's no 5 kings, but like this is us simulating the fact that there are no kings. Okay, probability that you will choose all red cards. Okay, well, over 52, choose 5, because that's my probability. How many red cards are there? 26, and we want all of them, all 5 of my cards to be red. So 26, choose 5, over 52, choose 5. What's the probability that you will choose exactly 2 black cards? So exactly 2 black cards. So how many black cards are there? 26. So I'm going to do 26, choose 2, and then plus, because this is still in the, or sorry, not plus, it's times, because it's all still in the same hand. This is all still there to be successful. How many non-black cards are there? Oh, that's my alarm that I'm supposed to leave. So let's see if I can finish this problem or two. What's the probability that we choose exactly 2 black cards? Well, 26 choose 2 is my 2 black cards. Then how many non-black cards are there? 26. I do 26 choose, I have to get to 5 cards. So it's going to be 26 choose 3 over 52 choose 5. Okay. So 1, A, B, and C are all probability. D, E, and F just say how many different hands. So I'm essentially just doing the top part. I'm not dividing it by 52 choose 5. Except the letter D says how many different hands are possible. Well, we've been using that this whole time. 52 choose 5 is how many possible hands there are if we just have 52 cards in a standard deck and I only get 5. How many different hands are possible if all the cards must be the same suit? Okay, well, they all have to be one of the suits. All of the suits have 13 cards, so it's 13 choose 5. That's how many possibilities. And then the last one, how many different hands are possible if 3 of the cards are of one suit and 2 are of the other suit? 2 are diamond, 3 are clubs. This is like the problem we did together in class. I'm going to put a little blank because there's going to be a coefficient out there. So I have to think about, okay, I've got 4 suits and I want to choose 2 of them. So this blank is that coefficient, 4 choose 2. That's how many suits I can choose. Okay, now once I choose the first suit, it's going to be diamonds. Now how many diamonds are there? 13. And we want how many of them? 3. 13, choose 3. Okay, now I choose a different suit. I choose clubs. There are still 13 clubs and I'm choosing 2 of those. Okay. I did ones like these in class, so you can also watch those. I am at my time limit, so I'm going to sign off. I'm going to close it off. I'm hopefully going to upload it real quick. And then if you have any other questions, let me know. Talk to you guys later. Good luck studying. Bye.